So let's go ahead and start by thinking about the simplest kind of situation where you can apply calculus with regard to integration. Let's think about motion, okay? And we're going to think about one directional motion. Say me walking to the right here. To the right for you, I'm not sure if it shows up on the to the right on the screen here. I'm walking that direction. What's the simplest assumption I can make about my speed if I'm walking to the right? Go ahead.
It's pretty close to constant.
Yeah, pretty close to constant, or let's just make it simple and say it is constant. Constant speed motion in one direction. If I allow myself to go back and forth, then I'd want to say maybe constant velocity. Say if I travel in the rightward direction, that would be a positive velocity. If I travel in the leftward direction, that would be a negative velocity, but it still could be constant. We're also going to talk about two-dimensional motion and maybe even three-dimensional motion sometimes in here. And then your velocity, for example, becomes something called a vector. Okay. Now, vectors are not going to be a big point of emphasis for us, but we will talk about them somewhat try to keep it at the basic level as possible. People who are in physics know a lot more about vectors than people who are not. But even if you're in physics, it's still worthwhile paying attention because there's still going to be subtleties that you may not realize. Okay. Well, let's say it's a constant speed. And even when it is a speed and not a velocity, people often use the letter v for the speed. In general, the speed is the absolute value of the velocity. Or if it's a vector velocity, it's the length of the vector, is the speed. But if we're only focused on one-dimensional, one-direction motion, the speed is the same as the velocity. In general, it's a function of time. The speed is in meters per second, say, for example. And the time would be in seconds, for example. There are other units, obviously, that can be included. And if it's constant speed, this function is a constant, say 3 meters per second. That's not really saying it's the number 3. It's saying its output always equals the number 3. It's still a function. For a given input t, I get an output v, but that output is always the same. It's always 3, no matter what v is. Graphically, how should I draw this? Or, yeah, horizontal line at 3. That's representing a constant speed. The output, the speed, the value v is always 3, no matter what t is. I'm interested in the distance traveled. For some reason, the distance traveled is commonly called s. I don't know why it's called s. That's a little confusing. It makes you think it's maybe the speed, but it's not. I will often call the distance traveled function dist of t to remind you that it's a distance traveled. However, today I will call it capital F of t. And you know, back in I don't know what it was, maybe 6th, 7th, or 8th grade, you learned a pretty important equation. Distance equals, what's it? Finish it for me. Rate times time. Speed times time. Rate times time. When the speed is constant, which it is here. Speed times time elapsed, if you want to be a little bit more specific. We're assuming a constant speed. Assuming a constant speed, which is what we are assuming in this problem. Then you can use this equation. Speed is in meters per second. Time elapsed is in seconds. The seconds cancel, giving you units of meters. The units of the distance traveled, S, is in meters. Again, it is typically called meters here, even though that's a little confusing because it makes you think maybe it's the speed, but it's not. Okay, we can figure this out here. That's pretty easy. The speed is 3 meters per second. And the time is t minus 0 seconds. T minus 0 because I started at time 0 and I ended at time t. I guess I didn't say that. That's my assumption. My assumption is I'm starting at time 0 and I'm ending at time t. Once again, the seconds cancel, leaving you in an answer 3t meters. Hey, couldn't I just written that answer right at the start? Did I actually have to go through this stuff about thinking about rate times time? I could have, couldn't I? I could just find an antiderivative of 3t plus c. Why do I not have a plus c here? Go ahead.
We're assuming it starts at 0.
Yeah, we're assuming that when t is 0, you haven't traveled any distance. S is 0 when t is 0. If I had a plus c here, and I plugged in s equals 0 and t equals 0, I could solve for c and I'd get c equals 0. Yes, the derivative of the distance traveled, capital F prime of t, is 3 is always equal to little f of t. So it's not surprising that we got 3t. The derivative of the distance is the speed. The integral of the speed is the distance. And if it's an integral of the speed, I guess we could interpret it geometrically in terms of areas too. Go back up to this picture. I'm about to do something a little confusing. Here's my explanation of how to get around the confusion. So here's a question. Is t a variable or is it a number? The answer is it's both. Because what is a variable? A variable is just a number that can vary using your imagination. You're imagining it to vary, but that's a useful thing to imagine. However, in a drawing, I can't make an animation in a static drawing. I have to pick a value of t somewhere, maybe right there. This is also confusing because I'm using t in two ways. This red t is labeled, just labeling the horizontal axis as being time in seconds. And the v up there is the speed in meters per second. This green t is I guess a fixed number in a static drawing. Though I could imagine it changing. For example, I could imagine it increasing, moving to the right. Speed times time is really the area of this rectangle here. The area under the curve. Because the height is 3 meters per second, and the base is t minus 0, t seconds, giving you units for the area of meters per second times seconds. The seconds cancel, giving you meters. The area has units of meters? Yeah, in my mind at least. In terms of the application, it does. Now, of course, literally on the piece of paper or on the screen, the area doesn't have units of meters. If you're literally measuring the physical area, you could measure the units in square meters or square centimeters or square inches or whatever. But in terms of the application, interpreting the area for the application, its units are meters. multiply the units on the axes, and cancel if necessary. Make sense? Confusion comes about for people because this stuff can have that kind of ambiguity, you know? You'd say, hey, the area is in meters, but you might say that doesn't make sense. Area is always square units of distance. Well, yes, but for this application, I'm thinking of it in a different way. And it's an okay way to think of it for the application. Since it's an area, since it's an antiderivative, I guess I could have also used an integral symbol instead of a derivative symbol. I could have also written capital F of t to be the integral of little f. Now I'm purposely stopping right there at the moment. Well, maybe I'll write a little more. If I did what's most natural and wrote like an indefinite integral without limits of integration of f of t dt, that is okay to an extent, though indefinite integrals, when you evaluate them, always have the plus c, though we know c is 0 for this example. But there'd be ambiguity there. By the way, the gateway is all indefinite integrals, and you must put the plus c there to get credit for each problem. So you're going to put a plus c on every single problem for the gateway. Just telling you that right now. And even though I tell you, a few people here and there will forget sometimes. Okay. So even though it's not completely wrong to put an indefinite integral of f of t dt, it's not yet ideal. If I'm thinking of this capital F of t, this distance traveled, as being that area, that's really a definite integral. From 0 to where? Well, if t is arbitrary, it would be 0 to t. Now, should I put a t here and a t there? I could, and in fact, many science and engineering teachers do, but I am now telling you, as your math teacher, don't. And if you do put a t here and here, I'll mark it not completely correct. On the test, you'll get docked some amount of points. Probably not many points, but something. Why? Why not put a t? Because of the conceptual emphasis. We're trying to emphasize that this function I'm defining with an integral has its variable as the upper limit of the integral. That's essential to truly understanding what we're going to do in these coming days and weeks. The true variable for the function capital F representing the distance traveled as a function of time is the upper limit of the integral, not the variable I put in these two spots. The variable I put in these two spots is often called a dummy variable. Why? Well, it's a little bit of a silly name to call variables like over here and here. I know the reason why they do it, but I mean, every variable in a sense is a dummy variable. It doesn't know what it is. It doesn't know what it represents. It's dumb. Right? Variables can't think. But by calling this a dummy variable, we're trying to emphasize it really doesn't matter what we call it. As long as we keep these letters consistent with each other, it doesn't matter what we call it. Don't pick T, don't pick F, don't pick D, pick something else. Common letters are U, V, W. I like using Greek letters. I love Greek letters. I think they're so beautiful. So I'm going to use the Greek version of T, which is the Greek letter tau. Oh, isn't that pretty? F of tau, D tau. Tau is just a fancy looking T. I do have a favorite Greek letter. I'm not going to tell you today because I want to let the suspense build. What is my favorite Greek letter? I might have told some of you already. Don't spill the secret. It's just so beautiful. That is an abstract way to write the answer. And its value, the value of writing it this way is maybe twofold. For one thing, it is going to emphasize something essential for this course. In section 6.4 of the book, something called the second fundamental theorem of calculus. It's a little confusing. Chapter 5's got the first fundamental theorem of calculus that tells you how to evaluate integrals. Chapter 6 has got this second fundamental theorem of calculus. Actually, some books switch the names around. And actually, I think switching the names around is actually the better thing to do, but I'm going to be consistent with our book. They call the second one the first one, and the first one the second one. What is what our books calls the second fundamental theorem of calculus? It's this. The derivative of this function, capital F, which you could also write as the derivative with respect to time of the integral that defines capital F. Make sure you use the taus instead of t's there. Is what? It is little f. It's like the integral, it's like the d dt and integral symbols cancel each other. Like a function and its inverse function cancel each other. E to the x and natural log of x, for example, cancel each other. It's like they make each other go away. And you're left with the integrand function. The d tau goes away as well. But this does beg a question. Should I put a t or a tau inside the parentheses there? Put a t. Yes, that's correct. You want these two variables to match. Don't put a tau. If t is the variable for capital F and capital F prime, then t better be the variable for the derivative of capital F, little f. So writing it this way allows us to emphasize the truth of this fact. And well, what's another way to emphasize the truth for this example? For this example, I could write this integral, I could replace f of tau with what it equals, which is 3, and use the first fundamental theorem of calculus. This thing right here is the second FTC. I'm about to use the first FTC, and you might wonder, is this allowed? Can I use both of them? Find an antiderivative of 3, like 3t. Do I need a plus c? No, because I'm doing a definite integral. Oops, that should be a tau. That's a mistake, sorry. So I dock myself a point. If I kept that a t. 3 tau. Tau goes from 0 to t. I do want the final answer to depend on t instead of tau. Tau is just an intermediate dummy variable. If I plug in tau equals t, I get 3t. If I plug in tau equals 0, I get 3 times 0. This does simplify to 3t. The same thing we got there. It had to. It seems too easy. It seems dumb to do this. And in a sense, it is for such a simple example. But there's more complicated examples where it's definitely not dumb to do this. This is a theorem. It's still true no matter what, no matter how complicated little f is, as long as it's a nice function like continuous. You can say this definitely still works, even if you can't find a formula for it. Maybe the formula is a new kind of function like Fresnel S or Fresnel C. Did I show you that Monday on Mathematica? Okay, it could be a new function that you've never heard of before, but this is still true and still valuable. I did use the first FTC right here. And yeah, I mean, you don't really need to use both of them in this problem. a problem like this that's as simple, but it's worth emphasizing that it still works. Let's up the level of difficulty now. Let's do a constant acceleration example. I'm still going to write down a formula for the speed. If the acceleration is constant, like say 2 meters per second squared, for example, and that will be the example I do, what would the speed be? If acceleration is 2, constant, what would the speed be? Integrate the acceleration. Right? 2t plus c, well, I'll take the c to be 0. So this is a new example. The 2 effectively has units of acceleration, meters per second, which is shorthand meters per second squared. The t has units of seconds. One of the seconds cancels. The final answer is in meters per second. The product 2 times t, since 2 has units of acceleration and t has units of time, the product has units of speed or velocity. But again, since it's one directional motion in a positive direction, say, with no turning around, in that case, velocity and speed are the same thing. In general, the speed is the absolute value of velocity. We're not going to do negative velocities today, maybe on Friday. What does the graph look like now of the speed versus time? It's a straight line with a positive slope. And its units would be meters per second squared. By the way, in the previous example, I could have graphed capital F as well. If you've got room in the previous example, the graph of capital F, distance traveled versus time, is also a similar looking graph, except with a slope of 3. And the units for the slope would be different. The units for that slope would be meters per second. It would be the constant speed in the first example. That's for the first example. The slope is what has the units of meters per second for that example. S itself had units of meters. That was distance. In this example, the slope has units of acceleration, but the variable v itself has units of speed. V is still in meters per second. T is still in seconds. Okay, so what's the distance traveled now? S equals dist of t. I'll just write the capital F this time. Can't do rate times time anymore, can I? Why not? Why can't I just do rate times time? Well, you can if you make a slight change, but if I don't make the slight change, I cannot do rate times time. Why not?
Because the speed isn't constant.
Yeah, the speed is not constant. It's changing. There's an acceleration. If you're moving to the right here in this situation, you're speeding up. Your velocity gets bigger and bigger. Your speed gets bigger and bigger. I can't do rate times time, but I can make a slight modification and call it average rate times time, or average speed times time. And if the speed is a linear function, the average speed is going to be the average of the extreme speeds, the lowest speed and the highest speed. Does that make sense? If the acceleration is constant, so that the speed is a linear function with a constant slope, the average speed, because this is a straight line, is the average of the highest and lowest speeds. Now, from time 0 to time fixed time t here, the lowest speed is 0. What's the highest speed? Over this interval of time. It's the second coordinate at this point. What would it be in terms of t? 2t. Yeah, it's that. Because that's what the graph, that's this function, 2t. So when the input's t, the output's 2t. Now don't be confused here. 2t does have units of meters per second, just like we said. Average speed is going to be the average of those two speeds, 0 and 2t. 0 plus 2t, add them up and divide by 2. Time elapsed is t minus 0. Both of these things simplify to t. I've got t times t, which is t squared. Hey, the derivative of t squared is 2t. Yay! It had to be t squared. Plus c, but the c can be taken to be 0. Because at time 0, we haven't traveled any distance. It had to be t squared. Yeah, the derivative of capital F prime of t is the derivative of t squared is 2t, which is little f. The derivative of the distance traveled is the speed. And I could also write capital F as an integral from 0 to t of little f of tau d tau. And in this example, if I evaluate that integral, little f of tau is 2 tau. Antiderivative with respect to tau is going to be tau squared. Tau goes from 0 to t, giving me t squared minus 0 squared, which is t squared. Same thing. Again, it seems silly to do all this stuff. Seems silly maybe in both cases, but it is worth it because it's going to generalize to harder examples. And it is nice to see that it still works out to be just what you would guess the answer would be if you were forced at gunpoint to guess or something, right? Speed's 2t. Tell me the distance traveled. You got 1 minute or I'll shoot you. Okay. If you had to guess, you'd probably say, okay, I'm going to anti-differentiate this and get t squared. You might not be sure what the plus c would be, but I hope you would guess t squared. I probably shouldn't use violin analogies, should I? Sorry. Oh, you're thinking about the constant acceleration formula? Yeah. Yeah, I mean, yes. If the acceleration is 2, if a is 2, 1/2 at squared is 1/2 times 2 times t squared is just t squared, yes. All right, let's now do an example where it's yet one more step up in difficulty. And not a constant speed, not a constant acceleration, but how about a constant jerk? Have you heard of the jerk before? If your function is distance traveled, or let's say in general position, which could be positive or negative, let's think in terms of back and forth motion. If your function s is position, its derivative is truly velocity in that case, not speed. Could be negative if you're traveling back and forth. Its second derivative is the acceleration, which also can be negative. Interpreting negative acceleration can be tricky, though, especially if you're traveling in the negative direction. The third derivative of the position is the jerk. I'm serious. It's called jerk. Why? Because when the jerk's high, your neck gets jerked, right? Travel in a car, hit the accelerator. I don't know. It's an engineering project. Look into it. When you hit the accelerator all the way, when you floor it, is the jerk positive? I'm guessing it is. Hurts your neck. It gets even crazier. The fourth, fifth, and sixth derivatives also have names. You know what they are, Michael?
I think it's snap, crackle, pop.
Snap, crackle, and pop. Rice Krispies. Your neck really, really hurts when you get to a positive pop. Acceleration is the rate of change of the rate of change. The pop is the rate of change of 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 the rate of change.
I think that was a close thing.
I think I said 6 of them. That's 6 derivatives.
Jerk is 3.
Snap, crackle, and pop, 4th, 5th, and 6th. Okay. Constant jerk. That's going to make the velocity, the speed, I should say, for our example now, be quadratic. Oh, let's say t squared. V still has units of meters per second. T still has units of seconds. The output has units of meters per second. It is V. The graph of this function is no longer straight. When t is positive, it's half a parabola. But the principles from the previous page still are true. S, the distance traveled from time 0 to time t, call it capital F of t, is still the integral from 0 to t of f of tau d tau. In this case, tau squared d tau. Geometrically, it's still the area under the curve. This area equals capital F of t. And also imagine this dynamically. If you imagine t to increase, to move to the right, the area is going to get bigger and bigger too. The distance traveled gets bigger and bigger, faster and faster, in fact. Now, this is a simple enough example still that we can actually find this area, but to find it most quickly does require the first fundamental theorem of calculus from chapter 5. Do the integral. 1/3 tau cubed. Tau goes from 0 to t, gives 1/3 t cubed minus 1/3 times 0 cubed, simplifies to 1/3 t cubed. By the way, I'm starting time at time 0 just to keep things simple, right? That's what you usually do, is you start time at 0. However, that is actually arbitrary. I could start time at some other moment, t equals 1, and declare that to be the starting time. And if I did, the lower limit would be a 1, and we'd be subtracting 1/3 times 1 cubed. We'd be subtracting 1/3 in that case. And the formula would be different. If I did start time at time 1, say 1 is right there, you'd have to kind of, get a running start, starting from maybe time 0 to have a positive velocity at time 1. But the way you pick the starting time is arbitrary, but 0 makes the most intuitive sense. And yep, we confirmed we got a function whose derivative is t squared is always little f of t. So we confirmed the second fundamental theorem of calculus with the first fundamental theorem of calculus, but the second fundamental theorem of calculus is still true, even if you can't use the first fundamental theorem to confirm it. And that fact that it's still true, this equation is still true, even when little f is complicated, is still useful. Even if you can't use the first fundamental theorem because this function is so complicated that you can't figure out a formula for capital F, or maybe somebody else did and they defined it after themselves, Fresnel S or Fresnel C, like we saw on Monday. There are other special functions like that that have other names. There's a Jacobi function. There's something called a gamma function. It's not defined in the exact same way, but a gamma function is another example of a special function. Nobody named gamma. Gamma is a Greek letter. There are Lagrange functions, Laplace functions. Probably there are Euler functions and Gauss functions. And yeah, Gaussians comes up in probability and statistics. You know, a normal curve if you took stats, sometimes called the Gaussian distribution. Normal curves in statistics, it's important to find areas under normal curves. In other words, to integrate them. But normal curves don't have simple antiderivatives. So you have to give them a name if you integrate them, a new kind of function name. But what is that? How is that helpful? Well, you could look up function values in a table somewhere or in a computer. But you also can approximate integrals. That's why we need numerical integration when the fundamental theorem of calculus is not helpful. It's always true, it's just not always helpful. That's a lot to take in. I will continue to emphasize those themes pretty much every day in these weeks ahead. Let's go ahead and approximate an integral. In the book, you often don't just see graphs, but you see graphs with graph paper, grid lines like this. F of t equals t squared, it's our constant jerk example. I might want to know what is the distance traveled by time 2, capital F of 2. Time is going from 0 to 2 here. It is the integral of t squared from 0 to 2. And now I'm just going to go ahead and use a t. I mean, I could use a tau, but I picked a particular number up there instead of a variable. So I'm okay using a t now. But a tau is not wrong. If you use a tau, it's not wrong. And that is the area under the curve. And if I've got a grid like this, graph paper, I could approximate that area by counting boxes, squares. What's the area of each square? Well, the base is 0.5 and the height is 0.5. Oops, sorry. Area of each square is base times height is 0.5 squared is 0.25. How many squares are there? Actually, in the previous class, I called them boxes. It's fine either way. Number of squares, could also call them rectangles. Let's first count whole squares. 1, 2, 3, 4, 5, 6 whole squares under the graph. And I also can match up approximate whole squares from pieces, like these two approximately give a whole square. I'm looking at the area under the graph. Those two, how many up? 1, 2, 3, 4, 5, 6, 7, 8. Maybe these two, 9. These two makes approximately 10. And these two makes approximately, say, 1/2 of a square. About 10.5 squares. Therefore, f of 2 would be approximately the number of squares times the area per square. And that comes out to be, I believe, 2.625. Oh, oops, mistake. 2.625 meters as your approximation for the area under the curve and the distance traveled from time 0 to time 2. The actual answer is 8/3, which is 2.6 repeating. That's the quote unquote exact distance traveled. Although in reality, in real life, you'd never know the exact speed, you only can approximate things. When I assume I've got a function like this, I'm assuming I've got infinite precision in my measurements, which is not realistic. But I can also be a bit more official about this and do Riemann sums to approximate the area. Left and right hand sums, for example. I can take each one of these intervals to be so-called subintervals of the entire interval, each with a certain width of delta t equals 0.5, 0.5. You should have done this in Calc 1, and then use labels for these endpoints. The first endpoint, 0, also called A, is labeled t sub 0. The next endpoint, 0.5, is t sub 1. The next one is t sub 2. The next one is t sub 3. The next one is t sub 4, which is the same as the right endpoint in this case. The fact that the last subscript is a 4 tells me I'm going to use 4 rectangles to approximate the area. If I do a left-hand sum, I could call it LHS for left-hand sum, or more typically in the book, maybe left for left-hand sum. And I also want to put in here maybe the number of rectangles, commonly called n. The number of rectangles matches the last subscript. I'm going to use 4 rectangles. And with the left-hand sum, what I do is on each of these subintervals is I pick the left endpoint to determine the height of the rectangle. So for the first interval, its left endpoint is 0. Go up to the function to get the height of the first rectangle, which is 0, which means there's really no rectangle there. It's a rectangle of height 0 and area 0. For the second interval from 0.5 to 1, pick the left endpoint, go up to the graph, and use that as the height of the second rectangle. For the third one, go up to the graph on the left endpoint and use that as the height of the third rectangle. And for the fourth interval and the fourth rectangle, use the left-hand endpoint to go up to the graph to determine the height of the fourth rectangle. The sum of the areas of those rectangles is going to be what we call left-hand sum. And you can see it's going to be too small because the function's increasing. In summation notation, I could write summation. I goes from 0 to 3, actually, of f of ti times delta t. That means add up f of t0 times delta t, t0 is 0, plus f of t1 times delta t, t1 is 0.5, plus f of t2 times delta t, t2 is 1, plus f of t3 times delta t. The f values are these heights. The delta t is the width of each rectangle. So for this example, this gives f of 0 times 0.5 plus f of 0.5 times 0.5 plus f of 1 times 0.5 plus f of 1.5 times 0.5. F of 0 is 0 squared, which is 0. 0 times 0.5 is 0. For the next one, I get 0.5 squared times 0.5. Then I get 1 squared times 0.5. And then 1.5 squared times 0.5. 0 plus 0.125 plus 0.5 plus, this ends up being 1.125. Put those all together. $1.75. 1.75 meters is an underestimate for the distance traveled. Remember, the exact distance traveled was 2.6 repeating. Our box approximation was about 2.6. The left-hand sum approximation is worse. But if we use more rectangles, we could make it better. If n was bigger than 4, it would be better. If we use more rectangles, we might get, like if I doubled n to 8, I'd get rectangles like this. And they would better approximate the area under the curve, etc. I wouldn't be missing so much area. Getting low on time. I don't want to completely do a right-hand sum, but let me tell you the idea. So I want to do one substitution problem here with you. For the right-hand sum, you'd use the right-hand endpoints to determine the heights of the rectangles. And what would they look like? The right endpoint of the first interval is 0.5. Use that as the right endpoint and the height of the first rectangle. The first rectangle for a right-hand sum would look like that. The second rectangle would look like this. I'm going to the right endpoint of each subinterval and up the graph to determine the height. And because the function is increasing, the right-hand sum is going to be too big. What will you get? I'd guess you'd probably get 3 or 4 something for the sum of those areas, which is going to be too big. However, if you average the left and right-hand sums, it's called a trapezoid sum, I bet it would be 2 something. We'd be pretty close. Not exactly right, probably, but pretty close. I'm not going to take the time to do that. It's in the book. There are examples. Trapezoid sum is called a trapezoid sum because it does correspond to areas of trapezoids that end up looking like this. Connect those points with straight lines and continue the trapezoid downward in each case.